Okay, we're going to spend this video doing a couple of problems from old tests just to give you a feel for what you might expect on the test or quizzes of your own. And it's all based on the idea that the full address is broken into two pieces, right? You have the most significant portion, which defines the chip select. All right, sorry about the handwriting, but apparently my handwriting isn't as good on a tablet as it is on the board. And then we've got these remaining bits, which are address lines going to the memory device. All right. And if you understand these pieces, you can understand exactly how to solve these problems. Because the problems I'm going to go through now, well, they kind of depend on an understanding. It's actually, they're really just very evil, true, false questions. Do you understand where to get the information for these three pieces? The full address, the chip select, and the address lines to memory. All right, let's take a look at this first problem. Can a chip select be designed for a 128K memory? Okay, that tells us one of the three pieces. This tells us the number of address lines going to the memory device, right? So lines to device. Now, how does it tell us that? Well, 128K is equal to, 128 is equal to 2 to the 7th, while a K is equal to 2 to the 10th. You multiply those two together and you get 2 to the 17th, and that 17, that tells you the number of address lines you've got. So if you're looking at the three pieces, so we've got the full address, you've got the chip select bits, and then you've got the memory device bits, right? Well, if we've got the number of lines, the address lines, we know this piece right here. We know the number of bits going to the memory. So we still have two more pieces to figure out. We still need to know the full address, the number of address lines, and the full address. Well, let's see if we've got that piece. If you look right here, I've got a processor with a 1 gig memory space, okay? So 1 gig, well, that's equal to 2 to the 30th. So I now know how many address lines are in the full address. I know that there are 30 address lines in the full address. Now the question is can I come up with the pattern of ones and zeros that defines the chip select? Well, hopefully that's taken care of with this piece right here. The memory has a starting address of 289A0000. So let's make a little room here. We know that there are 17 lines going to the memory address, right? And we know that the full address has 30. Now, if we make some room up here, let's see what this 289A0000 is. So 289A0000. That hexadecimal value in binary is 0010, 1000, 9 is 1001, A is 1010, and then we have 16 bits of zeros. Kind of ran out of room. No different than, I guess, doing it on the board. Now, the thing that we need to make sure is, remember that the low address, so this low address, this starting address here, needs to have zeros for all the bits going to the memory device. So I need to make sure that for a starting address that all these bits that go to the memory device, all of them are 0. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we do have, this can be a starting address because it has 17 zeros in the least significant bit positions where the memory address would go. That would be a good starting address. Now, 30 bits, the total number of bits needs to be 30 bits. Now, I've got 1, 2, 3, 4, 5, 6, 7, 8. I've got 8 times 4, or 32 bits in this address. But fortunately, the most significant 2 bits can be discarded because they are both zeros. We can delete the leading zeros. So we know that I have from here to here, these bits right here, that is my chip select. Those are my chip select bits. So, do I have all 3 pieces? Yes. The 128K, the 128K memory, that defines the number of bits that go to the memory device. The 1 gig memory space, that defines the number of bits going to the full address. And then this 289A0000, that defines a starting address that is okay, that is valid for the rest of the parameters. If, for example, we had, instead of being able to drop these 2 leading zeros, if there were 1s in those positions, we'd know that the address went beyond the 1 gig and we wouldn't be able to design the chip select for it. If there had been 1s in any of the positions for the starting address that went to the memory device, we'd also know that we couldn't answer this, or we couldn't design the chip select. But since all 3 pieces fell into place, the answer to problem number 1 is yes. Okay? Let's take a look at the next problem. Next problem asks, can a chip select be designed for a memory range 2D0000 to 2EFFFF, where the processor has a 16 meg memory space? Well, let's go back and figure out this 16 meg memory space. That 16 is 16 meg. 16 is equal to 2 to the 4th. A meg is equal to 2 to the 20th, so this is equal to 2 to the 24th. So we know how many bits the full address has. We know that the full address has 24 bits. Okay, that's good. And in fact, 24 bits, that's 6 nibbles, and both of these addresses up here are limited to 6 nibbles. So we're good with the address size too. Now, what about converting these guys to binary? 2D0000 base 16, that's the low address, right? So we've got 20010. D is 1101, and then we've got 16 bits of zeros. Get all of these down here. All right, so there it is in base 2. Now let's see what the high address is. Now the high address is 2EFFFF. Looks like a valid starting address, but let's take a look. So 2 is 0010. E is 1110. F is all ones, and we've got 4 of those, right? All right, so there's our low and our high address range. Now it looks like we should be able to draw our line here so that we can separate the memory bits from the chip select bits. But there's a problem. Remember, the chip select bits have to stay constant all through the range from low to high. And it turns out we've actually got 2 bits here that swap. The bit position, the least significant bit position for the chip select goes from a 1 to a 0. The second least significant bit position goes from a 0 to a 1. So it turns out there is no way to design this chip select because there are no consistent, the range for the full range, the chip select bits don't stay the same. That eliminates the possibility of being able to design this chip select. All right. So granted, we had 2 of the pieces. We had the size of the bits going to the, well, we had this number of bits going to the full address, and we had the number of bits going to the memory device. The problem is we didn't have a consistent number of bits going to the chip select. Let's try problem number 3. Can a chip select with a memory range from a low address of A50000 to a high address of A6FFFF be designed? Well, first of all, there's a couple of problems here. Number 1, we cannot figure out how many total bits we've got coming from the processor. This automatically eliminates the yes answer because there's no way to figure out how many bits are going to the chip select. Now, the question is if we can decide if there's not enough information or if the answer is no. If that range is valid, but we just don't have the full address, that would be not enough information given. If, however, there's some sort of a conflict like there was in the previous problem, we'd know that the answer was no. The only way we're going to figure this out is to just go ahead and do the conversion. So let's do it. So we have the low address of A50000 to a high address of A6FFFF. And so A5, so A is 1010, 5 is 0101, and then we've got 16 bits of zeros. Now we look at A6FFFF. Now, this one is suffering from exactly the same problem that the first one was suffering from. So we have the kind of, it looks like we could draw the line right here so that these bits go to the memory device, right? And these bits go to the chip select. The problem is once again, we've got these two least significant bits that are a problem. They don't stay consistent across the whole range. So the answer is no. If they had been consistent, if we were able to draw that vertical line and all the bits on the chip select side stayed consistent from the low address to the high address, then we'd have to answer not enough information given because we just wouldn't know the number of bits for the full address. Can a chip select be designed with a memory range from 5C0000 to 5DFFFF for a processor with 24 address lines? Well, it looks like we possibly have all of our information. 24 address lines tells you how many bits are going from the processor. Now we just need to figure out how many bits go to the memory device. Well, let's see if we can't figure this out. The low address is 5C0000 and the high address is 5DFFFF. Well, let's do the conversion. 5 is 0101, C is 1100, and then we have 16 bits worth of zeros following that. And then for the high address, we have 5, and then D is 1101, and then F's are all ones. All right, so do we have enough information? Well, look, if I draw my line separating the memory address lines from the chip select inputs, I've got everything on the right side of that line goes from all zeros to all ones, so that's valid. And on the chip select side, everything stays constant. All the bits that are in the low address on the chip select side of that line are equivalent to the bits on the high address for the chip select side of that line. So this side is correct. And as we said before, I know that I've got 24 address lines. Well, how many address lines do I need for these addresses? Well, I've got 4, 8, 12, 16, 20, 24. So the addresses even fit. So the answer to this problem is yes. All right, so let's move on to the next problem. Can a chip select be designed for an 8 meg memory? An 8 meg memory inside of a, well, we've got an address here, but we don't have the size of the processor. I do not see anything in this problem that gives me the number of address lines coming from the processor. I see that 8 meg, what is 8 meg? Well, 8 meg, we already know, is what, 2 to the 3rd times 2 to the 20th, 2 to the 3rd being an 8th, 8 and 2 to the 20th being a meg, which means it's 2 to the 23rd, which means that our memory device has 23 address lines. Well, we automatically know that the answer can't be yes. And the reason the answer can't be yes is because I know the number of address lines going to the memory. I know probably, maybe from the B4 address, what the pattern of ones and zeros for the chip select is, but I'm not sure. I don't see any way of determining the number of address lines coming from the processor. Just because we have the address doesn't mean I know that maybe there were some leading zeros knocked off, and maybe it's, instead of being, that's what, 8 nibbles there? Is that 8 nibbles? No, it's only 7 nibbles. So it could be a 28-bit address coming from the processor. Could be 32, just some leading zeros deleted. So we now just need to determine whether the answer is no or not enough information given. And so let's go ahead and convert this B400000 into binary. And by converting it into binary, we'll at least be able to see if an 8 meg memory can use B400000 as a starting address. So B is 1011. 4 is 0100. And then we have 20 bits of zeros. So we'll go ahead and add these 20 bits of zeros. I think that should be it. Now, what does a starting address need? Well, a starting address needs to have all zeros for the bits that are going to the memory device. And by looking at, 23 bits? Let's see if we can count these out. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. We only have 22 zeros. That last one right there, that one cannot be a bit that would be part of a starting address. It has to be a 0. And because of that, this can't be done. Not only is there not enough information, but the information we've got shows that it's not going to be possible. So we go ahead and say that no, this can't be done. All right, moving on to number 6. Can a chip select be designed for a memory where the processor uses 32 address lines? Cool, so we know the number of address lines from the full address. And the starting address is A90000000. It looks like we've got the opposite problem here. It looks like we've got the pattern of ones and zeros that might go to the chip select. It looks like we've got the number of address lines for the full coming from the processor, but we don't have the number of address lines going to the memory. Let's go ahead and do the A90000000. So 32 address lines, that's 8 nibbles. I do have 8, there's 8 bits, 8 nibbles in that address. So it looks like the address will fit. So probably the answer is not enough information. But let's go ahead and go, take this all the way out. So A9, and then we have 6 nibbles of zeros. So 1, 2, 3, 4, 5, 6. All right. Now, the question is, well, there really isn't a question. We do have the 32 bits, right? So that's okay. And we have a pattern of ones and zeros that could be used as a chip select. What we don't know is where to draw that vertical line. Now, as kind of a preview for what we're going to see in problems 7 and 8, if I did have this as a starting address, what's the largest memory I could put here? Well, remember from the previous problem, the starting address, all the bits for the starting address that are going to the memory device, they need to be zeros. So I have 1, 2, 3, 4, 5, 6 nibbles, or 24 bits worth of zeros there, which means that 2 to the 24 is the biggest memory I can have, which is 2 to the 4 times 2 to the 20th, which is equal to 16 meg. So I could, if needed, I could have up to a 16 meg memory in this starting position. But as it is, don't have enough information given. Let's move on to the next one. So, what is the largest memory that can have a starting lowest address of BB80000? Well, we got to convert that. So, BB80000. Now, just kind of as a side note, we really don't need to worry about the BB, because what we're looking for, like with the previous problem, is the number of bits that are 0 on the on the least significant portion of this address. We'll go ahead and convert those anyway. We'll go B is 1011, and another B is 1011. And then we have 8, which is 1000, and then we have 4 nibbles of zeros. 2, 3, 4. All right, so this gives us 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So there are 19 address lines which could possibly be used as bits or inputs for the address to the memory. So what's the size of the memory? 2 to the 19th is the same thing as 2 to the 9 times 2 to the 10. 2 to the 9 is 512, and 2 to the 10 is a K. So 512K, that's the biggest one we can fit in there. Now, what's the largest memory that can have a starting or lowest address of 8600,000? Lots of zeros there, huh? Whoops, and that's base 16, not base 2, it is base 16. So go ahead and make that look right. All right, so 8 is 1000, 6 is 0110, and then I have 5 nibbles of zeros. So that's 1, 2, 3, 4, 5. Okay? And if you count all the zeros on the right or least significant portion of this address, you'll see that there are what? There's 5 nibbles, that's 20, and then this last 0 right here coming in from the 6 nibble, that's going to be what? 21 bits. Well, 21 bits, 2 to the 21 is equal to 2 to the 1 times 2 to the 20th, which is equal to 2 meg. So the largest memory that can have a starting or lowest address of 860000 is there just, yeah, do we have, yeah, sometimes my eyes play tricks on me. So that's 1, 2, 3, 4, 5. Yes. So 860000. The largest memory is 2 meg. Now, let's make an assumption. What do we have here? There's 5, 6, 7. So let's make an assumption. The whole thing is 28 bits. If we were to assume that the actual size of the processor memory space is 28 bits, how many bits does that leave over? That leaves these 7 bits here. And those 7 bits can take on 2 to the 7th, or 128 different patterns of 1s and 0s. That means that actually, since the 21 bits that are to the right of that have to be 0 in order for this to be a starting address, that means that we actually have 128 positions where this 2 meg memory could fit in this processor's memory space. That's just a little side note, is that the number of bits that are left over after you take out the address bits going to the memory device, the ones that are supposed to go to the chip select, the number of bits there tells you the number of types of chip selects you could have. And that shows us the number of places we are limited to putting this memory inside of the full memory space. Hope that helped when it comes to solving some of the problems for this week's quiz.